4h58, ça fait tôt.
Oui, exactement. Mais bon. On attend 2-3 minutes après,
Exactement,
après l'heure.
Oui, on va attendre encore 1 minute et demie, 2 minutes, et puis la salle est pleine de notre côté, enfin pleine, en respectant les règles sanitaires. Les participants en ligne arrivent petit à petit.
Très bien.
Non, c'est une notabilité, ça met toujours en 9h40.
Quelle que soit l'heure.
Quel que soit l'orateur et l'heure. Et... 9h40. 10 minutes.
Okay. Okay, welcome everybody for this last afternoon session. Afternoon for us, for Martin, it's pretty early in the morning. So my pleasure to introduce Martin Lesourd from Harvard University. And I learned what BHI means, and he will be talking about the positive mass theorem with arbitrary ends. Please, Martin.
Well, thank you very much. So the BHI is a Black Hole Initiative. But anyway, it's a great pleasure to give this talk. The speakers and the talks have been wonderful. I've been trying to follow everything from afar, and it's worked very well. So it's a great privilege, and I'm very, very happy to be here. And I thank the organizers very much for inviting. Okay, so I would just like to start with some inspiration from none other than Misha Gromov, where excuse me, my headphones did something strange there. Yeah, I would just like to start with some kind of inspiring passages from Misha's 4 lectures that you can find. So as he says, so the most tantalizing aspect of scalar curvature is that it serves as a meeting point between 2 different branches of analysis, the index theory and the geometric measure theory. Each one of these theories has its own domain of applicability to scalar curvature with significant overlaps, etc. This suggests, on the one hand, a possible unification of the 2 theories, and on the other hand, a radical generalization or several such generalizations of the concept of a space with scalar curvature bounded from below. So I won't be talking so much in the spirit of the first passage, although I will make a couple of remarks with regards to this in the context of the positive mass theorem. And then he also says, unlike manifolds with controlled sectional and Ricci curvatures, those with scalar curvatures bounded from below are not configured in any specific rigid, but display an uncertain variety of flexible shapes, similar to what sees in geometric topology. Yet there are definite limits to this flexibility, where determination of such limits crucially depends, at least in the known cases, on 2 seemingly unrelated analytic means, index theory and geometric measure theory. So these are very kind of inspiring, insightful remarks. So today we'll obviously be focusing on the geometric measure theory aspect of scalar curvature. And we won't be talking so much about index theory, but as I will describe, the positive mass theorem has also been shown, or has a proof originally put forward by Witten, which uses index theory. And some of the things that I'll be talking about today has also been approached with index theoretic means, but the results are kind of different, and I'll emphasize that distinction. Okay, so I'm sure many of you are familiar with the positive mass theorem, at least the basic sort of statement. So the idea is you have manifolds that look like this. So these are the manifolds of interest. So basically, outside of a compact set, right? Outside of a compact set, say outside of this region, right? Then the manifold looks like a disjoint union of a finite number of ends, and the ends are diffeomorphic to R3 minus a ball, right? So that's you change colors. That's this region, right? And the ball is here, if you will, the boundary of the ball. And there's a coordinate chart in which the metric looks like that. So there's decay on the first, on the 0th, the first and the second order derivatives of the metric, where this is your metric of interest, and this is the flat metric. And Q is a specified decay rate that you need, or that you have as a convention of what you mean by asymptotically flat. But there are reasons for this Q. In other words, it can't be too small. If it's too small, if the decay is too slow, then lots of things don't work out. None of the methods that we have quite work. So you need some kind of decay to things to make things well defined and so on. But anyway, in this context, due originally to physicists in the 60s, Arno, Itesser, and Misner, you have a definition of mass, which in these coordinates looks like this. So you look at integrals over, if you like, a two-sphere. So that's this condition of these terms of the metric, and you normalize it by this with this term, and you take the limit as rho goes to infinity. So as these spheres get larger and larger, and I'm sure you're familiar that in that context, there's a theorem initially due to Schoen-Yau, and that has been proven in increasing levels of generality. But anyway, what our study does, so what we do is basically we don't study manifolds of the kind described above, but rather we will consider manifolds that look like this. So you have one good end, right? So you can think of this being an end, right? My rubber is too large. So you can think of this being an end, right? So this is the end where you have the asymptotically flat coordinates. And then out here, so let me make that a little neater. So out here you have all different kinds of structures that you don't control at all. So this could be a singular point, say, call point of incompleteness. So it could be for incomplete manifolds, and then you could have some other end here, but say that's some ends, but you don't know what they are, and you could have lots of topology, handles, etc., and you just don't know anything about what's happening on these ends. And then the question is, does the positive mass theorem hold if, say, I assume, so is there a positive mass theorem for these kinds of spaces where now the mass of interest will be when you measure the mass in this, right, in the end that you have, which you know is a good end. So M lives right where it can be defined. And then suppose, say you assume some restrictions on the scalar curvature of the whole space, then can you still prove that the mass is non-negative, say? Right? So that's the study. That's what we'll be doing. So we won't be doing the manifolds of the first slide. We'll be doing things like this. Okay. So what am I actually going to talk about today? So, I mean, first, I'm going to just quickly run through some basic things in the study of scalar curvature that's germane to this kind of analysis. Then I will talk about the modern proof of the classic positive mass theorem and describe how it fails, and you know, show how it fails to for this problem. And then once we'll have done that, we'll talk about some new techniques initiated largely due to Gromov. We'll talk about some motivation, a problem in conformal geometry, which we were initially trying to solve. And then, of course, we'll talk about the actual result of our paper with Ryan and Yau and the main ideas that go into it. Okay. So apologies for those who know so much about scalar curvature. I'll try to run through this rather quickly. But this slide is probably the least surprising to you all. So Ricci is defined here, and scalar curvature is a trace of Ricci. And one way to think about the scalar curvature, although I believe that Gromov doesn't think that this way has led to that many theorems. I think he mentions this in his 4 lectures. But anyway, this is if the scalar curvature is non-negative, then the volume of small balls are smaller than their Euclidean. So that's one way of thinking about it. If there's a product, then the scalar curvature is additive, and this is kind of a fundamental theorem due to Schoen-Yau in 79, and then generalized somewhat by Gromov-Lawson, different proof in particular in the 80s. So the idea being that if this admits non-negative scalar curvature, then you can find the connect sum, and that will also have PSC, as we call it, or positive scalar curvature. And the Schoen-Yau proof is a PDE proof. The Gromov-Lawson is an explicit construction. So, of course, some questions in scalar curvature, by no means all, consider simply which manifolds admit PSC or admit a metric with the scalar curvature bounded below, and also what are the geometric consequences, right? Now, of course, this is what will be. This is us, right? This is today. This is us today. That's that question we'll be looking at. And we'll be doing something a bit more general than this. Okay. So already for n equals 2 for surfaces, you can see that having non-negative scalar curvature everywhere can only happen in the presence of certain topologies, right? So, you know, just by the Gauss-Bonnet formula, you can see already that, you know, the Euler characteristic, say, is non-negative if the scalar curvature is everywhere non-negative. So already that leads to quite strong, very strong restrictions, of course. So more generally, for compact 3 manifolds, you've got Perelman's resolution of the Thurston geometry relation for three manifolds without boundary. You can reduce it to Perelman by Chodosh-Li and Gromov-Wilson, and in the compact spin simply connected, n is larger or equal to 5. You've got Gromov, Wilson, Rosenberg, Stolz. But that doesn't cover non-compact things, which is what we'll be looking at today. And you know, just as a rather enticing list, Gromov lists at least over 100 problems and conjectures, right? So you've got all these sorts of themes within the research of scalar curvature. You've got characterization for non-compact things. So this has been contributed to by members of the audience, by people in this room. So we have some experts, and then geometric inequalities. So this is what we'll be focusing us, and then rigidity, right? We'll talk about that, and then there's all sorts of other things that you can look at. So you know, convergent stability under these kinds of bounds, low regularity versions of this inequality. You could think about whether something admits a foliation by leaves which are PSC. You can think about the moduli space of metrics with PSC. So there's all sorts of things. And finally, this is my last slide of the introductory. We know that there's this kind of index theoretic approach. So this is the index theorem, and from the definition of the analytic index, and under some choices of how you set up your Dirac operator, you get the scalar curvature that shows up. And so if it has a sign, if it's a positive in particular, you know that the analytic index is 0, and therefore the topological index associated with D is 0. And that leads to all kinds of things, but and that was first how it was how it came in by Lishner-Horowitz in the 60s. So here we're going to do more of the second, so manipulate hypersurfaces. And of course, something that's very useful is the conformal formula for the change in the scalar curvature under change of the metric, which is a conformal change. So this is the formula you get for the change in the scalar curvature. Well, L of this can be read off from what's called the conformal Laplacian, which involves the ordinary Laplacian and the scalar curvature with this coefficient here. But of course, there are other things that you can do, and you know, I won't be talking about either of these two. So, but some people in the audience have worked on these. Right, so let's actually get to the heart of the subject. So the theorem, the classic positive mass theorem, tells you that a complete asymptotically flat three manifold with non-negative scalar curvature has mass non-negative and 0 if and only if G is flat. So this is the rigidity part, right? Because it tells you that this mass can only be 0 in this case. And this is the non-negative part. So we today will be focusing on this. We focus on non-negativity. And as I showed you, these are the kinds of manifolds that this theorem applies to. Now, by asymptotically flat, as I showed you before, you need some decay in some derivatives, and these are weighted Sobolev spaces that capture the decay. And then when you assume that the decay is sufficiently large, so I had it as Q before, but here I call it tau, then you have this ADM mass that's well defined and that looks like this. And an important special subclass of manifolds that you'd like to study, or that make the arguments, the geometric arguments, much easier, are what are called harmonically flat. So harmonically flat is simply an extra condition to asymptotically flat, where the metric is conformal to the flat metric, and the conformal factor is actually harmonic with respect to the Euclidean metric, right? So that's what that's saying. And when you have this, as I'll describe below, you can somehow simplify many of the arguments, because this the fact that the metric is conformally flat means that in a lot of the equations relating, say, the mean curvature or the second fundamental form of certain hypersurfaces within your manifold, you can kind of relate them to hypersurfaces in the flat space, in Euclidean space. And some of those relations and equations simplify when you have such asymptotics. Anyway, an important theorem in that context is a density theorem, as it's often called. And that tells you that actually, if you're complete asymptotically flat with non-negative scalar curvature, then for any epsilon, there exists a complete harmonically flat G tilde with the same restriction on scalar curvature, such that these are close in the relevant sense, with the scalar curvature remaining close in L1. So what that's saying is that, suppose I had a counterexample to the positive mass theorem for an asymptotically flat manifold. Well, I can always reduce it to something that's harmonically flat. So I reduce it to this. So this is a useful reduction, right? And I talk about this because this reduction no longer becomes possible in our case, and that's one of the main things that, well, I mean, that's one of the things that was a problem. So what's particularly nice about, so this is now I'm in the part of the talk where I'm overviewing the kind of modern version of the positive mass theorem, the kind of slick proof of the positive mass theorem. So Lohkamp found a way to compactify the problem using a very clever, but actually ended up being rather simple way of compactifying the problem. So what he shows is that if the scalar curvature is non-negative, and the harmonically flat manifold has negative mass, right? So that's what this is saying. Then what you can do, so this is what you start with, right? This is your starting point. And suppose that the mass when you measure here, so call it, say, m1 for this n number 1, suppose it's negative, right? Then what you can do is you can actually compactify these ends by using the conformal factor as a kind of way to bring the non-compact ends and to close them down. There is a question in the chat. Oh, yeah, there's a typo. This H should be before the K. My apologies. Anyway, so you can compactify the ends that you are not considering. So not where the mass is negative, and you can actually show that outside of some region, you can find a deformation of the metric, so that in fact you have something that's flat outside a compact set in the relevant distinguished end in which you had assumed negativity. Okay, but then once you do that, you're in a rather good position, because of course you can identify this and end up with a torus. So this region here is just what you get from identifying the sides of a big cube in the flat region, and then of course now you do that in a way. This whole process is happening in a way where the scalar curvature ends up being positive, and now you're rather happy because of course you have produced a PSC metric on the connect sum of, say, xn with a torus, where I've drawn xn here as another torus, but it could be anything, right? It's just the results from the compactification of the other ends, which in particular could have genus or whatever. So you now have produced a PSC metric on something which is a closed manifold and which is a connect sum of a torus with a closed manifold. And of course, by geometric theorems that such a thing doesn't exist, and that's your contradiction. So that's just what I was just saying. So the classic theorem of Schoen-Yau is that such a manifold doesn't admit PSC. Right, doesn't admit PSC, at least from 3 to 7. That was already done in 1979, which was generalized in 2017. But anyway, the argument, I only include it because it's rather quick and it kind of shows, it will give us a taste of what's to come. So if you have something that's orientable with PSC and n is less or equal to 7, then any non-zero homology class, so integer homology class in Hn-1 is representable by a collection of compact oriented hypersurfaces, each of which admits PSC. So what that should really say is you get a stable minimal surface when you minimize in the homology class. Right. So this is that's the regularity part of the theorem, and that's something that's very classical. And then once you have the stability inequality, you can look at variations of the surface. So you can have some surface, you look at some normal vector field, you vary the surface normal to this. You vary the surface in the normal direction by some phi nu, where phi is, say, the speed of the variation, and then what you get is the stability inequality, which reads like this. And then using the Gauss equation, you can rewrite some of these terms, and you end up showing that because these are good terms in the way you've assumed them, this is actually ends up being 0 because it's a minimal surface in this case. You can show that you get this inequality on sigma n-1, right, which is your hypersurface, and that actually, by looking at the conformal Laplacian, which is what I showed you a few slides ago, you can show that this in fact admits PSC. So this is an overview of the SLIG proof. You start with something general, you move to something that's harmonically flat. That was the reduction, right? Where you had some nice form of the metric outside a compact set in each end. Once you have this, then you do the Locamp procedure, right? So this is what happens here. That produces something flat outside a compact set, and you've compactified the other ends. And then you identify the sides of a big cube and end up with a torus in a way that preserves the scalar curvature positivity. And then this you can rule out by the geometric theorem I showed you above, proven by Schoen-Yau. So this is the classic. This is the classic slick version of the modern proof of the classic theorem. Now I'm going to change gears a little bit here. Bear with me for just a second. I'm going to change gears, and we're going to put the positive mass theorem behind us. We won't be thinking about it anymore for at least a few slides. And I want to think about conformal geometry, because that's actually how we came to the problem with Ryan and Yau. So a classic theorem of Cooper says that if MG is simply connected and locally uniformly flat, then there's an immersion into Sn, which induces the locally uniformly flat structure on M by pullback. And moreover, this map is unique up to conformal diffeomorphisms of Sn. So this naturally leads to the question of simply, when is phi a diffeomorphism onto its image? And as far as we could tell, the first time that was studied in the context of scalar curvature was by Schoen-Yau in a beautiful Inventiones paper of '88. And it was recently resolved by the work of Chodosh-Li. And then we gave a different proof, which was more in the spirit of the original ideas of Schoen-Yau. And that's what will motivate the positive mass theorem with arbitrary ends, which I introduced in the first few slides, which you might have said, why are we interested in such a theorem? Well, anyway, the way to think about this one is you can think about the conformal Green's function. So the Green's function for the conformal Laplacian at a pole, with pole at P. So this is the operator of interest. This is what I mean by the Green's function. And what happens, which is kind of remarkable, and this was used very much in Shane's resolution of the Yamabe problem. What happens is that the blow up of the Green's function can be used to your advantage to construct something that's asymptotically flat by using the Green's function itself as a conformal factor. And what that does, so remarkably, the Green's function has this property that you can use it as a conformal factor to create something asymptotically flat. And then once you've done that, you can just, you know, by say some stroke of imagination, you can just say, well, why don't I consider the mass associated with the asymptotically flat end that I've obtained by blow up using my conformal Green's function? So you might say that's a rather strange thing to do. Why should the mass obtained by blow up of the conformal Green's function, why should that be interesting to look at? And I think that's where this proposition for me was first so striking, such a beautiful result. Well, it tells you that actually if MG is just some complete manifold with non-negative scalar curvature, and phi, say, is a conformal map from M to Sn, which of course is the kind of map that we're interested from the slide I showed you before, then it turns out that the injectivity of this map is an if and only if with the positivity of the mass obtained by blowing up the manifold with its conformal Green's function. So there's a beautiful link here between the mass of the blow up and the so how do you define the energy? Well, that's more of a typo, really. It should just say the mass, right? It's just the mass. So E was the language used in the original paper, so I stick to that. But E is really just the mass. So you could just say M. So then what they conjectured is said, okay, well, suppose you had some complete non-compact Riemann manifold with non-negative scalar curvature, and then you just assume that one of these ends has an asymptotically flat structure. So this distinguished end has an asymptotically flat structure. And then you say, well, is it the case that the positive mass theorem holds for such a space? So if the scalar curvature of the whole space is non-negative, but these ends are arbitrary, you have no idea what they're doing, you know, there could be all sorts of things, you just don't know, then is it still true that the mass is non-negative? And if it is, then you know that this mass is non-negative or positive, and you get injectivity of the conformal map. So this is kind of how I would summarize the various contributions in the literature. It's a bit confusing. So Schoen-Yau established the injectivity of the map using other means, that they don't use it via a positive mass theorem, but rather by looking more directly at the problem. For n is greater or equal to 7, and for n is less than 7, they have some assumptions, right, from 4 to 6, and from n equals 3, they don't actually include a statement, but they show that it follows anyway from the positive mass theorem with arbitrary ends, but they don't prove the positive mass with arbitrary ends. And in a previous paper with Ryan and Yau, we showed that it actually also follows from what you could call the torus conjecture or the Garrosh conjecture. I think that's how Chodosh-Li describe it. But basically, that's the conjecture that you can't put a PSC metric on the torus connects sum with X. We saw that for closed X, but now this is for non-compact X, right? So it's for arbitrary X. So for complete non-compact manifold X, is it the case that you can still put a PSC metric on the connect sum of this with the torus? And so we show that the injectivity actually just follows from that geometric statement. And that geometric statement we prove for n equals 3, but we also prove between 4 and 7 under some assumptions, but those assumptions end up being preserved in the procedure. So that gives a restricted version of the injectivity of the map. And then Chodosh-Li actually, in a beautiful paper, which also shows that you can't have PST metrics on closed aspherical bases, which was, of course, generalized recently in the talk that Chow was giving. But anyway, in that first paper, if there's so in that first paper, they actually show the excuse me. They show this theorem without assumptions between 4 and 7, and thus yield the first full proof of the what you could call the Liouville theorem. And then we prove the generalized version of the positive mass theorem with arbitrary ends, and so we give a kind of proof more in the spirit of Schoen-Yau in this later paper. So the final result that you get, which is now a theorem, is the following. So you have a complete manifold with non-negative scalar curvature. If you have a conformal map, then this map is in fact injective. Okay, so that was the motivation from conformal geometry, and now I'd just like to talk about some recent results on non-compact manifolds, which will kind of herald for the ideas of the proof and the techniques, and which will make them more natural in the view of what's been done. So mu bubbles is a terminology. I think it comes from Gromov, I'm pretty sure, but not everyone adheres to it, so I've stuck to it. But anyway, so there are some beautiful recent papers by various people using mu bubbles, not just Misha Gromov himself, but others too. And one that was kind of quite recent by Jintian Zhu. He shows that if you have an orientable complete open Riemannian manifold with non-negative scalar curvature and admits a smooth proper map to the product of the torus with R, then with the line, and in fact you have this rigidity. So so it's isometric to the flat torus, to the flat torus times R. And then, of course, in a wonderful contribution, Chodosh-Li and Gromov independently showed that you have this rigidity, right? So for closed aspherical manifolds, 4 or 5 manifolds, for you can't have PSC, and if you have non-negative, you have Ricci flat, and you can actually prove more things. But anyway, they show that these kinds of bases don't have PSC metrics. And then more recently, they even have this kind of this more recent statement, which kind of combines. I haven't studied the proof in a lot of detail yet, but it seems that it combines some previous ideas and some other ideas in metric geometry, and anyway, so that's the even more kind of complete picture of what happens in those dimensions under these kinds of assumptions. So this is the other, right? This also uses mu bubbles. So this was the theorem that I was describing before, the one that implies the injectivity of the map. So PSC is not allowed on manifolds which look like Schoen-Yau cross S1 connects some with an arbitrary manifold. So Schoen-Yau I'm not going to define, but basically it comes from the Schoen-Yau paper to a great extent. In order to do this inductive procedure where you minimize in homology classes at each step, you need the homology of the manifold to be organized in the right way, and that's precisely what Schoen-Yau means, and that's a terminology due to Gromov as well, I believe. And basically what they show is that, so in particular, I mean, the torus is a Schoen-Yau manifold, but you've got lots of Schoen-Yau manifolds that are not the torus. And anyway, the point is that this obviously implies that the torus doesn't admit PSC, of course, which I don't even write because this is obviously a lot more general. And what's beautiful, I think, about this paper is that it kind of, or at least, this application of mu bubbles and the stability inequality that's in there was really what got us we had been trying to prove the generalized positive mass theorem for a while, but it was reading this paper of Chodosh-Li that really got us started. Anyway, so we have a kind of similar theorem, but using minimal surfaces, and that has drawbacks. It has some advantages, but it has some drawbacks. So I suppose the advantage is that we actually look at SYS. So these Schoen-Yau should connect some xn without this S1 product. So from that standpoint, you cover a kind of wider class of manifolds. But the main drawback is that you actually have this kind of condition which tells you that rho balls, so rho metric balls, are lambda Lipschitz contractible, right? At least for between n 4 to 7, we have to make this assumption to get the theorem. So it doesn't prove this one without assumption between 4 and 7. So that was the drawback. But of course, on the positive side, you sort of cover a wider class of manifolds, but somehow there is probably a statement out there which rules out this condition, but so far I haven't been able to prove that. And then of course I just wanted to mention some what I think are quite extraordinary, beautiful results by Ji and Wang, where now it's minimal surfaces that are being used as opposed to mu bubbles, but Mix-Yau minimal surfaces, as it were. And of course, this is a beautiful result, recent results, which I think combines lots of ideas in the subject. But anyway, so those are some kind of results for non-compact manifolds, recent results, and in particular, this sort of space doesn't admit PSC. And so the landscape, as it were, looks a little like this. You have the original PSC results of Schoen-Yau in 79. You have the original Schoen-Yau PMT, so that's the positive mass theorem. Then you have Locamp, which offers the compactification in 1999. I should have mentioned first. You have the right 88 paper where they put forward the positive mass theorem with arbitrary ends. That's a conjecture. They prove that means phi is injective. But then in 1999, Locamp reduces the PMT to the geometric statement, and there's no PSC metric on the torus, or the torus connects some. And then we show that actually this geometric theorem is, if X is just arbitrary, then that implies the objectivity of the map. So that's the first paper, and then that was shown by Chodosh-Li in 2020, and then we proved the kind of a generalized version of the positive mass theorem with arbitrary ends, which now implies the positive mass with arbitrary ends, and therefore implies the injectivity of the map, but through a different argument than what was just outlined. Okay, so finally we get to the main subject. I think I have about 20 minutes left, more or less. So that should give us ample time to actually get on with the results and some of the ideas. So as I'm sure you've seen, and some of you know very well, mu bubble, you're not minimizing area anymore like you were doing in the Schoen-Yau 79 proof, but you're minimizing the kind of weighted area minus weighted volume over some open set of interest that you end up selecting and choosing based on topological assumptions that you make on your space. And I think one of the great things about mu bubbles, or the reason why they're kind of so interesting, is because they allow you to handle regions that would otherwise pose problems when you minimize. So in particular, suppose you had an end like this, right, and this was really shrinking down to infinity, and you had some cycle here, and you minimize in the homology class of this cycle, then the issue is that your minimizer runs down the tunnel, as it were, and disappears in the limit, right? And of course, remember that minimizing was the key idea behind the Schoen-Yau proof. You minimize because then you obtain something that's regular, that's embedded, and that has the stability and equality that's satisfied by the virtue of being a minimizer. And then once you have that, you can play around with the stability and equality and prove various things about the hypersurface. So if your minimizer is disappearing because you have some non-compact end, then the whole proof just stops working from day one. And the wonderful idea to handle these kind of ends, but this could also be true of a boundary, say, is that you construct a function h, which will go to negative infinity or positive infinity, and that will contain, as it were, the regions of interest. So suppose you had a manifold of this kind. If h is going down to negative infinity or positive infinity here, what that really does when you look at this functional, that's going to contain all your minimizers to live within this region. And if they live within this region, and you can prove, regularity and existence of a minimizer, etc., then you will have something embedded, and you will have something that obeys some stability inequality. Now, this trick seems almost too simple. I mean, it literally is saying, well, okay, you want to contain yourself within a region of interest, so why don't I just put h is going to infinity and have a volume term that will repel any surfaces from ever getting close, right? So if there's a surface that's going to be close here, then it's going to be penalized by the functional, by the choice of h, right? So it seems like such a simple thing to do, and it seems like that shouldn't be allowed to work. Magically, choosing h well enough leads to a stability inequality that's powerful enough to prove theorems. And I think that's the main point to take away, I guess. So yeah, on the general use of new bubbles, so I mean, you've got to prove existence and regularity of minimizers, but that's not so hard in view of the geometric measure theory that's already available. The first variation leads to a mean curvature that looks like this. So you have a prescribed mean curvature equation. The second variation looks like this. So that's a little more complicated to handle. But if u is just equal to 1, then this goes, this term disappears, this term and this term disappear. And so you see that the relevant terms become this whole term here and the scalar curvature. And so it turns out, because all of these other terms appear with a sign, so it turns out that if this, well, I should also include this, right? These are the important terms. So when you have this inequality, then you see that you end up with this inequality on sigma. Sigma is the mu bubble of interest, right? So remember, this is so what that means is that suddenly you have a conformal metric on sigma, which is PSC. And so then the challenge is now, how do I set up something which obeys, I'll use a different color, how do I set up something which has this condition which is satisfied, and that this little h is organized suitably that it picks out minimizers that you want. And by that I mean minimizers that will allow you to kind of argue a contradiction in some way. Okay, so this is actually the main theorem we have. So from 3 to 7, right, in dimensions, complete manifold with non-negative scalar curvature and one asymptotically Schwarzschild end. I'll describe what that means. It's a slightly more stringent assumption than asymptotically flat, but it's weaker than harmonically flat. Anyway, then the mass of that distinguished end is non-negative. So what you see is this kind of theorem, right? This is the theorem essentially. But actually, it turns out that it follows from a more quantitative statement, which you could think of as maybe stronger than the previous slide. So this is the quantitative theorem. So you've got U1 and U2 are neighborhoods of infinity. So if this is my asymptotically flat end, and these are the other ends elsewhere, then U1 is, say, everything out here. Right, and then U2, say, is everything out here. Right, and what it's telling you is that if there are no points of incompleteness in the D neighborhood of U1, so that rules out, for instance, if I had, say, if I had something that, right, I have these other ends, they could be doing whatever. I don't know what they're doing, but suppose that I had some, had some point of incompleteness here, say, right? So this is now incomplete. Then what I need is this distance in the metric G from U1, right? So I need this distance here to be larger than D, right? So that's what the first assumption is saying. The second assumption is saying that the scalar curvature is non-negative in the D neighborhood of U1. So I think that's one of the most surprising things. I mean, when you see the proof, it's end up being not surprising, but as a statement, it's something that wasn't anticipated, at least when you look at the generalized positive mass theorem, or at least, the conjecture of Schoen-Yau from '88. So in particular, what this is saying is that the scalar curvature only needs to be good, if you will, or non-negative in the D neighborhood if you want. So it's really localizing the non-negativity of the mass to the distinguished end. In particular, the scalar curvature elsewhere, right? So the scalar curvature, say, on these ends, right? Here, the scalar curvature R could be going to negative infinity, right? And that's allowed. That's kind of amazing, because in the PMT, right, you needed non-negative scalar curvature everywhere, and now suddenly you're allowing the scalar curvature to be arbitrarily large and and have the wrong sign, so long as it's far away from the region of interest. But then you also need a kind of quantitative positivity. You need it to be sufficiently large on an annulus. So in between U1 and U2, on this kind of little annulus, you need it to be sufficiently large. And if you do that, then you get what you want, namely that the mass is non-negative. So I have another picture here, which is maybe slightly neater than the picture I drew. So this is the largeness assumption, right? You have the largeness assumption on the annulus. You have no points of incompleteness in the D neighborhood. So that's what that's saying. And you see how the bound on the scalar curvature that's required includes, right, the distance in a quadratic way, which you could have expected from mu bubbles. You see this kind of quadratic decay all over the place, and you see the distance also that's happening, or that you see between the thickness of the annulus, as it were. Right. So I'm going to have to go a bit quickly now, but the original argument was done for n equals 3, and it was generalized by Rick Shane for n from 4 to 7. But the basic argument is that if you assume the mass is negative and you have this harmonic flatness, right, which is this extra decay condition, then you can show that the coordinate planes actually lead to barriers, right? So you can find a minimal surface between two large planes living in the asymptotic region. So this is what this is saying, right? H is 0. This is a minimal surface along this tube, and here this is a coordinate plane. So xn, say, is equal to a0, and xn here is equal to minus a0. So that's what you mean by sigma, little sigma a. A is kind of the height along here. That's what you call a. And little sigma is, say, the radius of this guy, right? So then what you do is you say, okay, well, let me take a sequence of these. So you build a sequence as little sigma tends to infinity, and you show that this sequence, which I've drawn here, right? So this is as a little sigma as it goes to infinity. You show that it converges to some minimal hypersurface. And then because it's a minimizer at each step, you show that the stability inequality at each step leads to a stability inequality. So there's a stability inequality here. There's a stability inequality here. And you show that this leads to another stability inequality here, right? And you do this, and then what you show is that this leads to a contradiction directly for n is equal to 3. But I'm not going to go into that argument. And then for 4 to 7, what you show is that the stability inequality leads to the existence of a conformal factor. So the stability, well, I should say, first of all, the mass of the of the minimal surface, right, but in one dimension lower. So this minimal surface turns out to be asymptotically flat. That's key. More than asymptotically flat, it actually has 0 mass. And then you use the rigidity part. Excuse me, sorry. Then you use the stability inequality that's inherited on the on this hypersurface to show that there exists a conformal factor, which changes the mass to something negative. But of course, that gives a counterexample to the positive mass theorem in n-1 dimensions. And so you're done. But there are complications from the arbitrary ends. So in particular, the compactification argument of Locamp, right, uses this harmonic flatness, but the density theorem, where you move to something harmonically flat, this is no longer available when you have these arbitrary ends, because you now have to solve a PDE on these arbitrary ends, which you don't know how to do if you don't assume anything on the arbitrary ends. The original argument that I showed you above, it might not work, because when you do this minimizer, you've got some ends now, and you don't know if your minimizer is being sucked into the ends. And there is a tantalizing fact, which is that if we look back to the slick proof, with the geometric version of what we wanted, namely no PSC on torus connect sum, with something arbitrary is known, right? This is the work of Chodosh-Li, right? So this works, but you can't reduce it to prove the positive mass theorem. So what we do is we set up H is going to go to negative infinity, say within a D neighborhood of U1, where U1 was this region of infinity. And what that does, well, that will just cancel the ends, right? All of these ends will no longer be relevant for the problem now, because as H is going to negative infinity, and we look at this functional, then your minimizers are going to live north of this red line. And if they live north of this red line, you don't need to worry about what's happening below the red line anymore. And then the main issue is, are you going to be able to set up H and set up the stability inequality in a way that's strong enough to run a kind of contradiction? So these are the mu bubbles we obtain, right? So H is going to negative infinity here, say, and that will penalize any surface from ever venturing too close. And then C little sigma is the coordinate, right? Is a cylinder associated with the coordinate planes I drew before, and this is a kind of curve in 3 dimensions. At least this is a curve that lives along the boundary. So remember, what we had was something like this. We had the 2 coordinate planes, right? So this guy here is gamma little sigma, and C sigma is the cylinder, and then the actual surface itself is little sigma A, where A is chosen. So obtaining the mu bubbles using this kind of problem is doable. What you get is regularity, and you get a prescribed mean curvature. As in the equations I showed you before, when you have the mu bubble, you get the mean curvature equation. And then what you do is you build a sequence of these things. So this is my picture for the sequence. You build a sequence for larger and larger little sigma. And what that does is each time you're penalizing anything from ever venturing too close to where you've cut off essentially the rest of the manifold. And then you want little h to be going to 0 away, right, as you go large enough, because you want these guys eventually to become minimal, if you will. And what that leads to is a sequence of mu bubbles, right? That's simply what you get, but you get these mu bubbles with a boundary. And at this point, you might say, okay, well, it looks like you're, you've got something going, but what about the actual inequality? So the setting up of H has to work with the stability inequality that you get from the mu bubbles. But it turns out that all we need for this problem, but this we have to show, is that you will only really need this. And so that's where H is constructed, and that's where the largeness in R comes from. So when I showed you that you had this condition with the D on the denominator and this other D and the distance, so that comes in by the construction of H. So this is this little sigma. So there's a notation issue here. I shouldn't have used little sigma because that was used above for the radius of the coordinate cylinder. But anyway, that's how you construct H. And now just a word about asymptotic to Schwarzschild. So what that really means is that it's not harmonically flat, but it's kind of like, you can think of it as being asymptotic to the Schwarzschild metric, right? So I'm not going to write the Schwarzschild metric, but this is the conformal factor that you get in the Schwarzschild metric when you think of Schwarzschild as being conformally flat. So okay, so what do you actually have to do? So you have to build a sequence of mu bubbles, but you have to show that the mu bubbles eventually produce something nice. And so you have to control sigma infinity, which is the limit of these mu bubbles. So in the harmonically flat context, controlling this sequence takes quite a bit of work, but it exploits the good asymptotics of G, namely the harmonic flatness. And this is what I was saying when this harmonic flatness lemma, the density theorem I mentioned initially is very helpful in this context. But in the arbitrary ends, you don't have this. So you kind of have to cheat a little bit, or you have to kind of think of it. You pretend it's harmonically flat, right? So you write it as something that's conformal to the Schwarzschild metric, where now psi is the conformal factor to the Schwarzschild metric, and then you treat G as conformally flat to lower order terms. And you have to kind of control these lower order terms to show that in fact you do get something which is a graph. Eventually these mu bubbles, they converge to a graph sufficiently far out, and that takes some work. And then finally, the stability, you have to kind of incorporate two aspects of. So I know I'm running a little bit out of time, but I promise to be done within the next 3, 4, maybe 4 minutes. But the key with stability, right, is that before you. So I told you that to make mu bubbles work, you need to choose H so that you contain the relevant regions of interest, right? You annul the effect of having an end or the effects of having a boundary, etc., and you're able to contain your problem. But that you're going to lose something. You're going to lose something in the stability inequality. And the question is, did you set up H sufficiently well that you can still make your stability inequality work for you? Well, in this case, you need something extra. You don't just need that. You actually need to minimize with respect to A, which is where you chose your mu bubble along the coordinate cylinder, right? So remember, the picture was, sorry if I'm making you seasick here. The picture was here, right? A is this, so A is along here, right? This is where A lives. So it's kind of the height of where you're doing your mu bubble. So you minimize both the mu bubble functional, which gives you the stability inequality, but then that's actually not enough. You also need to minimize with respect to A. And what that does is that gives you, so the stability inequality ends up being kind of a bit of a mess. because now the stability inequality involves a boundary variation as well as a bulk variation. And the bulk variation and boundary kind of look like this. So these are the terms that you get. And then you have to show that this stability inequality is good enough to get you your contradiction. Now, what is going to be the form of your contradiction? Remember, in the ordinary or in the classic proof of the positive mass theorem, so not the slick proof, but the classic proof, for n equals 3, you showed that it was direct, right? There was a direct issue with the stability inequality in the spirit of a Gauss-Bonnet type argument. Whereas here, you do a kind of induction argument. So you show that there's a counterexample to the PMT in one dimension lower. And you do that by showing that the mass of the relevant hypersurface is 0, but there exists a conformal factor that leads to something with negative mass, and this conformal factor is controlled in various ways. So in order to do that, you need to solve a PDE, and what you need to solve a PDE, but the only thing you have is the stability inequality and the decay on the mu bubble. But fortunately, the stability inequality is strong enough to get you your the existence of a conformal factor which behaves in the right way. And it does take some work to show that this stability inequality is good enough on the limiting mu bubbles to get your conformal factor, which produces something with negative mass in one dimension lower. So this was me trying to show you some of the terms that crop up. So you'll recognize some of these terms from the usual stability inequality. These are some extra terms you get. Some extra terms you get, and you really do. This is the decomposing the variation. So another thing I should say is that the variation isn't just normal. You need to vary kind of in different directions depending on where you are. But I think these details we can kind of just maybe go to just the last slide. So just the basic structure of the argument is that, right, so sigma infinity is the limit of the mu bubbles is asymptotically flat. Moreover, it has 0 mass. That takes some time to show because you don't have these very nice asymptotics anymore. You don't have harmonic flatness. But there's a way around that. And then you show this sigma infinity admits scalar flat metric with negative mass, and that comes from the stability inequality, which is what I just showed you before. And then you get this quantitative version of the theorem. And then by taking D sufficiently large in the quantitative theorem, you end up getting the positive mass theorem for just complete manifolds. And in particular, what's interesting is that in the quantitative theorem, because you don't care about what anything happens beyond the D neighborhood of U1. So U1, remember, was the region of infinity, and the D neighborhood was what happened within right? Because you don't care about what happens beyond that, then the scalar curvature could be doing absolutely whatever you want, and that doesn't matter at all to the argument. Okay, so I'm sorry I run out a bit of time, but thank you very much for your attention, and apologies again to the organizers for running about 5-6 minutes over time.
Thank you very much, Martin, for this exciting talk. Are there any questions? No.
I don't know if that's a good sign or
It's, I bet it is a very good sign anyway. So, well, if there are no questions,
maybe I have
there is one.
Yeah. Can you go back? So your statement of the main results.
Yeah.
No.
This one, the quantitative theorem, or just this one.
No, the gluing any end.
Yeah, so this is true for this is the positive mass theorem for arbitrary ends, and this is the quantitative theorem that produces the theorem of the previous slide.
Okay, this is a possible. I want to ask. This is a possible to perturb a mu bubble or minimal surface to get a smooth surface in higher dimension and to generalize this result to any dimension. I mean,
yeah.
maybe-
So yeah. So I should have mentioned that the 7 restriction is of course the standard restrictions that is due to the regularity issues that happen for 8 and above. So your question is,
yeah, maybe in the Schoen-Yau's work use some modification on near the singularity to show the generalized test for the positive mass theorem. This is possible to use this Schoen-Yau's work to generalize your result to any dimension.
so first of all, I should say that that's an extremely interesting question, and it's very much a subject of investigation. However, unfortunately, I can't give you an answer. It's
Okay.
I'm sorry to tell you. The short answer is I don't know. I don't know if mu bubbles can behave in the way that you might hope that minimal surfaces might behave to make this proof work. Certainly, if you can show that mu bubbles, if you can show that, say, the Schoen-Yau arguments or something.
Because actually, Schoen-Yau just use the conformal Laplacian. Yeah, just study the conformal Laplacian and perturb the minimal surface near the singularity, because he used the conformal Laplacian to deform the eigenfunction of the conformal Laplacian to deform the singularity. This is
there are so there was a question in the chat. So just to finish on that point, I really don't know how to handle higher dimensions. Not only do I not know, I don't fully understand the minimal surface arguments. I don't understand how you would try for mu bubbles, but it's a big avenue of research, and any results of the kind mentioned, maybe perturbations using the conformal Laplacian or whatever, would be amazing. That would be wonderful. But I can't give you any kind of result or anything like that.
Thank you very much.
Yeah, it's a very good question. It's very, very hard question. So there's a question in the chat. So can you explain a little more how you send the mass to the point P using the Green's function of the pole P? Yeah, so the Green's function decays. It decays. It blows up like 1 over x, where x is the distance from the pole, right? So if let's go back to the Green's function. So there's a question in the chat. So, right, so the Green's function looks like this on approach of, say, plus a constant plus something else. And with this is ignoring normalization. So what you see is when you use this as a conformal factor, then this 1 over x term creates something that blows up, right? Because right, and that stretches the metric, and so that produces something asymptotically flat. And then when you look at the next order term, if you will, so you look at this new asymptotically flat metric, then the mass right? If you have something that's harmonically flat, say, so U, say G is equal to U to the 4 times delta, then if U is, say, 1 plus if it's 1 plus A over X, etc., then you get that the mass is actually equal to A, right? So when you use the blow, when you use the Green's function, so I might have got a formula. Let's see. Yeah, no, right. So when you use the Green's function, so this is a different A. I should write it like, say, B or something. B, right? Then what you get is when you evaluate the mass of this new metric, right? Of this metric, then you get something that's where the mass shows up as being the next term in the expansion of the Green's function. So not the 1 over X term, but the next term along. So B in this expansion. Does that clarify?
Okay, are there more questions? Okay, if this is not the case, we thank you very much for this very nice talk, and also for waking up so early for us, right? So, and hope to see you soon somewhere. Okay, we resume at in 45 minutes for the next talk. Thank you very much, Martin.
All right, well, thank you very much for the opportunity and the questions. Thank you.